welcome and thank you for joining us today as we discuss the Temporal .NET SDK, which has recently become generally available. My name is Irina Belova, and I'm a product marketing here at Temporal. If you would like to stay more connected with Temporal or ask any questions to our team, check out our community page at temporal.io/community and join nearly 10,000 fellow engineers on our community Slack. The link will be in the description of the recording. We would love to chat with you and learn more about what you're working on. All right, now I would love to introduce our speaker today. It's Chad from Temporal Engineering Team. Hello, Chad. And with that, I will hand it over to you.
Hello, thank you very much. So today we are going to talk about .NET and what the investments Temporal has made in .NET, the .NET SDK, and how you can leverage .NET to use Temporal in very awesome ways. So specifically what we're going to talk about today is we're going to just do a quick table setting of what is Temporal, just a real quick, just so that the pieces, the .NET specific pieces we talk about later are not a surprise to those that may be new. If you're familiar with Temporal, you may already know this, but it might be an interesting brief way for you to see it from a different view. And then we're going to talk about Temporal.NET, what the .NET SDK is, how awesome it is, all the neat things that it can do, and how you can leverage the Temporal features via C# and via .NET. Then we're going to get into the more fun part, which is talking about the challenges we had building it, some of the things that we have to do to stay within Temporal durable execution environment, but still leverage all the benefits that .NET developers expect. And finally, if there's some time, we'll have some QA, like Irina mentioned. All right, so starting off, what is Temporal? So Temporal, as many here already know, is MIT licensed framework for durable execution. The co-founders have created similar things in the past, and it's culminated to this point. The way Temporal works is it's essentially workflows based on an event source model to allow resumption of code everywhere. It has a server component that is essentially a event storage database and test distribution mechanism that communicates with end workers that end users run to actually run durable software in a distributed way. So the main concepts are, like I mentioned, that server. Then you have workflows, which are the deterministic, durably executing piece of code that can essentially run anywhere and in several languages, one of which is .NET, which we'll talk about today. Activities that are delegation to general purpose code that doesn't have the constraints that a workflow might. And then the SDKs, which are ways for you to write this code and are frameworks within that allow you to write this code and debug it and work within it. So specifically, what is the Temporal server? It's MIT licensed server written in Go. It persists all the events to the database and orchestrates task distribution to the workers. This server, of course, can be run locally, as can the UI, but the way a lot of users use it is via the Temporal Cloud. And the Temporal Cloud is the Temporal hosted equivalent of this server that is very easy to adopt. Obviously works well with .NET and all of our other SDKs, but you still get to run your own code. So it doesn't run any code for you and doesn't have any security concerns that way. And of course, we offer a local version of the server for development purposes and testing purposes. So what are the SDKs? Well, the SDKs are libraries written in several popular languages that allow you to write your own workflows and activities and make them durable. And so we have SDKs, primary SDKs in Go, in Java or other JVM languages, TypeScript, Node.js, Python, and now .NET. And the Go and Java SDKs are our oldest and and they have been around longer, but the newer SDKs in TypeScript, Python, and .NET all leverage a common Rust core. The SDKs are complex. They're not just smart clients with some typing and whatever. They're idiomatic language implementations of the advanced temporal state machines in order to deterministically run workflow code with coroutines. And then they also do offer the smart client aspect, the worker daemon aspects, and some of those others. So the SDKs are quite complex, and they're complex to the point to where it's unreasonable to rewrite this state machine and some of these complex machinations in every language. So it was done once in Rust, and now it's leveraged in 3 of our 5 primary SDKs. So that's Temporal in a nutshell, your ability to write long-running, durable workflows, and then several of the components that make that possible. But many familiar with Temporal are already familiar with these concepts, but now let's get into Temporal.NET itself. So this was a project that we started knowing that there are many .NET and C# developers out there that would like to leverage temporal and durable execution in general. In fact, the durable execution framework, the durable execution concept is already seen in .NET in some other ways. So the .NET SDK is now GA. It is out there. It is solid. It is on par with every other SDK as far as features, quality, and in some cases more, and we can discuss that later. But it does, so if you're familiar with Azure durable functions, or even journal brains for that matter, but more for like durable functions, then you may be familiar with the idea of how temporal works. They actually have a very similar genesis in that the durable functions leaning on durable tasks, which was written by Temporal's co-founder, and things like that. So the .NET SDK has the framework for a worker daemon that allows you to write workflows and activities using .NET. And it also provides a typed client, which allows, and we'll get into later some of the neat typing that .NET allows you to do. We work very hard on our SDKs to make sure that they fit in the language idiomatically. So it will feel very much like writing .NET software, not necessarily just a general purpose temporal thing, but it'll feel very native if you're a C# developer already. And it technically supports really old versions of .NET, but we still leverage modern features, which is something we try and do in our SDKs to make sure we work for everyone. .NET, perhaps uniquely more to .NET than just about any other runtime, is the idea of extensions. There are several Microsoft extensions and not standard library extensions to .NET that are effectively part of the standard library because they are so commonly used. Dependency injection, metrics, and others are like this. So we offer extensions that support those extensions because they are so commonly used. Like I said, they might as well be part of the standard library. And we put in the extra work and the time to make sure that when you're writing a workflow, it uses the regular .NET task framework, and therefore we wrote a custom deterministic task scheduler to ensure that cooperative multitasking is deterministic inside your workflow so you can do all your normal concurrency as you would outside of a durable environment. So you'll note that it says .NET package add pre-release. You no longer even have to have pre-release now that we launched GA. So I just need to fix that. But in general, it's in NuGet. It's available to everybody. Please use it. So let's go over how to do certain things in .NET and in C#. So the first thing is defining an activity. So an activity is general purpose code. In this case, I want to make a HTTP call. So here's an example of an activity making an HTTP call. Activities in Temporal are retried by default. They're customizable, so on and so forth. To mark a C# method as an activity, you simply put the activity attribute on it. And this is an example of making an HTTP post, but you'll notice that it uses a cancellation token right there out of the activity context. That's how we propagate activity cancellation through the server. Different languages do this in different ways that's most idiomatic to their language. And for .NET developers, they'll be aware that cancellation tokens are the way to do it here. And it's not listed in here, but there's also a heart beating mechanism. And it shows an example of throwing a non-retriable error in a certain exception clause case. But in general, this is do whatever you want code. These are activities that are meant to be composed by temporal workflows, and they have no extreme constraints on them. But workflows do have constraints, and they must be worked within. So the primary constraint of a workflow is that it must be deterministic. To give my 1 minute, how does temporal work? Essentially, it's event sourcing. So if you run through half this code and then the worker crashes, the process dies, whatever, it'll be able to resume exactly from where it left off because all of the pieces that have already executed are already memoized in the history, and it runs up until where it left off. But it looks like magic, and it looks like it's just magically resuming code. The only way that works is if the code is deterministic. So the second time through the code looks exactly like the first time through the code. And we have ways to enforce certain levels of determinism in different SDKs. But in general, this is a representation of what a C# workflow might look like. So a workflow class, and if you're familiar with Python, it follows a lot of similar approaches and kind of similar approaches to the temporal Java SDK with some notable differences. But basically, you mark the class with a workflow attribute. You mark the primary function or the primary method with a workflow run attribute, and then you can write your deterministic code inside of there. You can use asynchrony and things like that. There are some places in so certain things in .NET are not allowed due to logic constraints, non-determinism things. So you can't do any like thread sleeping or like accessing disk or IO or anything like that. But some parts of the .NET Task API are also not usable because they're not pluggable. So you can't use task.delay here in the current version because .NET doesn't really support plugging that. Now, they actually just added, like last month, a new time provider API. But in general, if you want to sleep, you'll have to use the temporal provided sleeping mechanism as opposed to the .NET provided one, because ours is durable. You want to sleep for a month, you can sleep for a month. That timer is durable and persisted on the server. But other things you can use, other task things you can use, and you'll notice that normal await semantics are supported in here. But you'll see that there's invocation of activities, and you'll see that execute activity invocation is actually just looks like a normal call, a normal Lambda, but it's actually a Lambda expression. So we extract at runtime that activity call out, and we actually tell the server to invoke it. So it doesn't invoke it directly, it's telling the server to invoke it, but you get all the benefits of all that type safety for your activity definition, which is very powerful. And of course, we serialize the requests and response and stuff, and we use common .NET JSON serialization to do that. And you'll see here that there's also a signal and a query here. Now, this doesn't demonstrate our newest feature, workflow update, because workflow update's not quite stable yet, but it is there if you want to try it unstably. But this demonstrates how to do a signal and a query, a signal being just an async method that can't return a response because it is a unidirectional signal and it is marked with the workflow signal attribute. A query here, I actually demonstrated it being a workflow query attribute on a property. Queries are read-only, and if you don't really need to do any logic, making it a property is normal. But you could totally make it a synchronous method otherwise if you prefer. So that's the basics of workflows inside of C#. And if you're familiar with temporal and other languages, this will make sense that it's just a C# variant of it. But you'll see you get to run normal code. You can run a normal try catch. You can for loop, ifs, whatever you'd like, so long as it deterministically runs, it's safe. But in order to run all this code and for the server to communicate, it needs to be running in a worker. And a worker is a daemon that runs workflows and activities. And this is a probably more convoluted than it even needs to be example of how to instantiate a worker and start it. There's really nothing to it. You instantiate the activities and provide it the workflows, and then you just run it. And then you can ignore the boilerplate code about, Control-C support and such. But in general, it just runs. And for those of y'all that may be familiar with .NET generic hosts or ASP.NET hosts, this actually fits into that API perfectly. And you can use those extensions to fit into that API. So you can also have dependency injection inside of your activities and have your activities instantiated each time they need to run if they're like transiently scoped or similar. So so that's how you run a worker, and it's a normal daemon, and it could fan out as much as you could imagine, because Temporal is built to scale that way. And you can see there at the top that it connects to a client. Well, that client can be used for other things. In this case, this client executes a workflow. So here is in connecting to a client and invoking a workflow. So you'll note that the arguments are well typed, and that workflow inside the start workflow async call, that workflow is a Lambda expression that, like the Lambda expression for executing activities, does extracts what that call is and tells the server to do it with full type safety. It doesn't run it right there. So that purchase record is actually getting serialized to JSON. It's actually telling the server to run that workflow. If this workflow were written in another language, you could still have a stubbed type of interface representing that typed version of that workflow. And a lot of our larger polyglot companies do use Temporal that way. So they might have a Go workflow that they invoke from .NET safe with type safety, or the inverse, .NET workflow invoke from Go. It doesn't matter. And since it's just using JSON and workflow names under the hood, they're all compatible. So you can see here that it starts a workflow, but you can also signal a workflow just as easily, cancel workflow. You can see that querying is just as simple as accessing that property. In this case, if it were a query that was a method, it would be the same as calling the method. And again, those that are familiar with Lambda expressions, which we'll talk about later, that's how this is solved. And I'll get into that in a little bit later. But that's the basics, create an activity, workflow, activities and workflows, run the worker that invokes the activity and workflows, and then execute those things via a smart client. Obviously, it can do so much more. And again, it is a full-featured SDK in the sense that .NET is one of Temporal's primary SDKs. Every feature and every other SDK is in .NET and then some. And so it can be relied on as such. Not to mention, it is incredibly high performing. So other features that the SDK has, among others, workflow scheduling, full-featured workflow scheduling with the actual complex workflow or schedule model that lets you customize the exact intervals and do backfilling and all the advanced stuff you may be familiar with scheduling. An open telemetry extension, so it plugs right into the existing .NET open telemetry and .NET activity libraries, not to be confused with workflow activities. ASP and generic host support. So if you're used to running daemons in that way, which many .NET developers are, it'll work just fine. Same with that dependency injection, which is very popular in .NET. It will work through there. And then we have extensions for metric, custom data conversion, end-to-end encryption, like all SDKs, a full testing framework, replayers, so on and so forth. So finally, and most interestingly, if you ask me, we get into the challenges of building it. So I have one of the best jobs, because whenever you get to design something like this, you get to design it from scratch. And so we do it as a team. And basically we say, okay, there is a language and a runtime people are familiar with. How do we apply temporal rules to this language? And these rules are like, you have to have deterministic cooperative multitasking. You may have to integrate with this Rust core. You need to be high performing. You need to have all these kinds of serialization and error management rules and things like that. And so we have to mix what temporal concepts are with what the language concepts are in the most idiomatic way for that language's users. And that's what makes our SDK so powerful and so user-friendly. So the first challenge is we have to integrate with Rust. So the core logic and state management, and actually the gRPC communication with the server and everything is built in Rust. And it is powering our Python and TypeScript SDKs in addition to our .NET SDKs. But in Node.js, If you want to write a Rust extension, they have a nice high-level framework called Neon that helps you with that. In Python, if you want to write a Python Rust extension, they have nice high-level frameworks in Python for that, or in Rust for that, Py03 in this case. However, in .NET, not so much. There are a couple of burgeoning ones, but they didn't do everything we needed to do. So that means we have to go lower. We had to write a low-level C FFI into our Rust core. And for anybody that has ever had to do, in this case in .NET, it's called pinvoke, but anybody that's ever had to interface with a C library directly from a higher level language, know that it can be scary. It requires paying a lot of attention to ownership and lifetimes of objects, making sure you free things in the right way, especially something like temporal, where this is a daemon and it's expected to be long running. We cannot have leaks. We cannot have unreferenced memory. And the thing is with these CFFIs, even in .NET, if you're accessing something that may be no longer there on the Rust side, we're not talking a nice little friendly .NET exception. We're talking a seg fault. We're talking a serious crash. So we paid very close attention to every little detail of the ownership and lifetime to make sure that we do not go beyond the pieces. So we have the Rust side that generates a C header. Then I use the CLang pinvoke generator to generate C# code, and most of the pieces pass between because our server expects them to is protobuf. So a lot of the advanced structs we didn't need, but we still needed structs. And then we use some of these advanced interop services in .NET to keep like pointers open longer than the .NET garbage collector thinks they're needed, and to properly use pointer handle disposing to free things on the Rust side, because on the Rust side we have to use unsafe Rust to tell Rust to stop reference counting in some cases, so and not to follow its comment drop procedure. So this was a interesting challenge, but a fun one for sure. The next one is type safe invocations. So it is very important for us in our SDKs to allow type safe remote invocation. If you are in a workflow, you should be able to call a defined activity remotely using your own known typed definition of that activity. This catches so many errors. It helps with IntelliSense. There's so many obvious ways. Sure, you can drop down to strings and objects if you want, and we offer that kind of flexibility, but most users want to use type safety. So originally what we did, and what you'll find in some things like durable entities and such, is we used a dynamic proxy concept where you either had to have an interface or virtual methods, and we would use like the Castle dynamic proxy object. And you may be familiar with this if you're a JVM person on what we do on the Java side, but we made a dynamic proxy, and then your invocations would be intercepted and then turned into remote invocations. That's kind of bad because we can't put in all the options that are invocation specific, but then you could do method references, but .NET doesn't do method references well. So our original incarnation of the .NET SDK actually looked like this top snippet here, where it's like .ref.run, so that we could, with type inference and with generics, extract the types out, make sure that the parameter is right and such. But it had a lot of limitations. And it was made clear to me by everybody in the .NET world, no. The proper way is to use Lambda expressions. And it was made clear, to our entire team that. And so we discussed and we decided, yes, this is a much better approach. So now we're using Lambda expressions to make type safe remote invocations. So you will see now it is much better. That run async call can have just about any argument that can be serialized and via temporal serialization, and you can actually make the invocation. So it could have multiple parameters, though we don't recommend it. It could use records, and you'll see that we extract at runtime the information in. So obviously, Lambda expressions, for those that are familiar with .NET, cannot do everything. That's actually a good case for us. That means that Lambda, you can't just go running any arbitrary expressions, because we expect a certain AST, a certain body in there. But it means it's a little bit limited, but for our use case, this worked great. So this was another challenge. And then the last challenge that we ran into with .NET was how to support deterministic tasks. So tasks are .NET's futures, awaitables, promise, whatever you might want to call it. It is their abstraction of asynchronous work. And many languages, Go notwithstanding, allow you to customize the scheduling of their coroutines. .NET does to a point, but only kind of. So we wrote a custom task scheduler to ensure that the .NET tasks are deterministically invoked in certain order. But the .NET task framework and idea and different methods only sometimes use the custom scheduler. Other times they use the default scheduler. The default scheduler of .NET uses one big static class thread pool that you can't even customize if you wanted to. There is no such thing as a custom thread pool in .NET. So the problem is that at different times and in seemingly inconsistent ways, the .NET API will decide or will default to using the default scheduler, which goes on the thread pool, which is bad. It's non-deterministic. And other times it will use the current schedule, one that's in context, and which is good. And they even have analyzers that will warn you if you're accidentally using the current context, but we want the inverse. We want you to only use the current context. And so there were certain ways that we could handle this. And we handle this with documentation and other durable frameworks that require in .NET that require deterministic execution have this same set of requirements. It basically tells you, don't use task.run, use task factory start new. Don't use this API because you're not allowed, use this API. And we have that too, but what we also wrote is an event listener. And an event listener in .NET can listen to certain events that different frameworks inside of .NET choose to emit. And in this case, the task framework does emit every time it schedules a task. And so we add an event listener to catch that. And if you are in a workflow, if you're not in a workflow, we get out quickly because this has performance concerns. But if you're in a workflow and you jump out of the workflow thread, we will now fail you. And that's a very powerful way to keep determinism safe. If we were able to have a sandbox in .NET, we definitely would, but we can't. There's no reasonable sandbox that exists in modern .NET. There was older ones with app domains and such, but they've all been deprecated. So since we can't have a sandbox, this is the best we can do as far as keeping you from accidentally using threaded libraries. And so we will catch it and we will fail you. And it does not have a significant performance impact on the rest of the threading that your system may be doing. So there's also a new concept I mentioned of the time provider API was just merged like a couple of months ago. And we'll also leverage that, but that doesn't really help older .NET versions. We also plan, and it is not developed yet, and we plan here and in many other languages to have an analyzer. .NET, probably also more than any of our other SDKs, supports and encourages static analysis. And they have lots of tools for developers to write static analyzers. And we will be writing one to catch mistakes of like accidentally sending something on a separate thread. There are other things you can't do, obviously, like you can't access random and stuff, but we can't really limit that. So that's where the analyzer comes in. But this was our last big challenge for .NET was to make sure that you could still use the task framework and still compose a task. So if you want to run 20 coroutines deterministically doing concurrent work inside of a workflow and have that be durable software that can resume on any computer during a crash, we now support it with this. And that's what makes it powerful, but that was an interesting challenge. So those are the three primary challenges. And we found these challenges to be very, very interesting during development. So that's kind of a wrap on what Temporal is, what Temporal.NET is, and then I would say our three primary challenges that we hit as we were doing development that I thought would be interesting to discuss. So now I will open it up to maybe any questions or any further discussion that anybody wants to have about any specific details.
All right, thank you, Chad, for the awesome presentation. And we hope all you found this information to be valuable for you. And now we're going to move into the Q&A session. We have some questions, and I will start with this one. Hey, Chad, say if there's thousands of long-running tasks in flight, does it cache all this in memory or otherwise?
Sure. So basically, that's up to .NET. .NET, obviously, there's overhead for having a bunch of tasks, but if you have 1,000, that's no big deal. It's what you do in the task that Temporal doesn't really cache. I mean, it does cache as an optimization to resume workflows on the same worker so that it doesn't have to replay from scratch. But otherwise, we don't cache the local variables specifically. So if you start 1,000 tasks, that's fine. If they replayed and started 1,000 tasks, that's fine too. But now if you started 1,000 activities, that will show up in history. So whether a task is in memory or not is up to .NET, not up to Temporal. And the answer is yes. There's overhead for coroutines in every coroutine implementation. And I can actually, if you want, Irina, I can actually just jump to a few of these if that's easiest for you.
Yeah, sure. Thank you.
Okay. So does Temporal support for native AOT? If .NET supports it and pinvoke still works with it, yes. We try very hard when we write these SDKs to do nothing special. So if the .NET compiler works with it with its native libraries that we use, then yes. I personally have not tested whether pinvoke works in the native AOT thing, but I suspect so. Having said that, I haven't found a good use case to AOT in our cases because the .NET runtime is very performant here. How is .NET SDK compared to other languages performance-wise? Great question. I'm glad you asked. Let me say, awesomely. I don't have exact benchmarks, and the main reason why we don't often publish these benchmarks is everybody's workflows look different. So you can't really just blindly say, oh, this one's fast, blah, blah, blah. But let me put it this way. Let's discuss our other 4 SDKs. You have Go, Java, TypeScript, and Python. Now let's just drop TypeScript and Python, Node.js and Python for a minute, because we all, I think, can understand that they have performance limitations with their single-threadedness or GILs and such. But Go and Java are very performant and have been optimized. .NET, from what we found, is just as performant as those, and even better in some cases. So it's probably just as performant as Go in a lot of cases, but Go is not as type safe as .NET because .NET gets to leverage a lot of generics, and even if Go generics were applied, Go generics are not very powerful like .NET generics are. And also we get to control the task scheduling a little bit more. In Java, there was no virtual threads when Java SDK was developed, so it uses a thread for all of its coroutines inside of a workflow. Granted, it reuses them and such. So you could say that for the combination of type safety and performance, .NET may be the highest of all SDKs. That might be a reasonable statement. Having said that, all the SDKs are very performant. You should choose the one that fits the language you're authoring in best, and probably not for performance because of how horizontally scalable workers are. Can you use when all? Absolutely. And let me just make sure real quick that that's not one of the ones that secretly uses the default scheduler. And I put the logic constraints in there. Okay, so it's when any actually will use a default scheduler, but or could in some cases, but when all and when any for the most part absolutely can be used, no problem. And that's what makes it powerful. And that's why we work so hard to make it fit within the task framework, is so that you can use when any, you can use data flow, you can use all of these asynchrony things, and it looks like normal code. Let's see, when the main server and workers, what external monitoring is necessary across stacks since it's durable? We expose metrics. So I won't speak to the server. It also exposes metrics, and so does the cloud team. But the .NET, the SDKs all expose metrics, and you can choose to push it to an open telemetry endpoint, expose via Prometheus, or we put in extra work to make sure that metrics from the Rust side can get pushed into a .NET diagnostic metrics source if you so choose. So you could even customize the metrics, collect them, do whatever you want, react to them as they're being recorded, because unlike Python and TypeScript, which have a Rust overhead to their invocation, the pinvoke overhead is almost none. So it is very high performant for Rust to call back to .NET and .NET to call back to Rust. So we do expose metrics directly, which is very, very cool, very cool. And you can use them that way. Again, what most people do is they just throw a Prometheus port on it or a OTel gRPC endpoint and do it that way. So James asks, given the query and signal functionality of the workflows, can you compare and contrast Temporal to an actor framework like Orleans maybe? Yes. So absolutely. So actors require that you use messages for just about everything. And this is actually a general Temporal discussion, not really a .NET one. And I have a lot to say here, but the main thing is that Temporal offers imperative code. And being able to do code imperatively not only makes it much more easy to reason about, but there are certain things you can do that you have to work around in an active framework. For instance, try starting a bunch of activities in a loop inside of an active framework. It does. And then try and collect like the first 3 responses and do something. You'll start to see when message passing starts to fall apart when you actually need imperative algorithms. Same with like different forms of try-catch and composability. Basically, it's like asking, why would you not always write actors instead of normal code? The reason we write normal code is because actors are difficult to reason about and difficult to apply your algorithms to. And there's a whole much more to be said about that, but it's not really .NET specific. Joe asks, so how does Temporal Server scale when you go from thousands to millions of long-running in-flight instances of workflows? So not really .NET specific, more about the Temporal Server, but I can say, there's lots of docs on scale, and of course our cloud scales, theoretically infinitely to the point to where millions of workflows, no big deal. Though of course you'll have to set up the servers in certain ways to handle that, but it is built to heavily scale. But I won't get into the details here. But millions of workflows, it's a thing. It's plenty common. Running workers. Leverage .NET background jobs. Absolutely. It is built to actually, so the .NET generic host support and ASP.NET host support is built to plug right into that. So if you use if you use host services as background jobs, Temporal Worker could just plug right into that. However, for scalability reasons, usually people just run their worker on its own inside of a process. They don't try and mix a bunch of concerns and processes because it is very normal to scale out workers as different processes on different containers and whatnot. Let's see, with query, you can ask something workflows, but doing kind of pulling. Is there a way to avoid pulling? Yes, there is. We call it workflow update. It is currently in a pre-release state. It is not so it is not yet stable, but the code is there for it, and in certain local environments you can turn it on. We're planning though to make it available in the future. But yes, so that is on Temporal's roadmap to bidirectional interaction with the workflow. There are other ways that you can do interesting ways of pushing back activity results on ephemeral task queues. I won't get too detailed into it here, but yeah. So Paul is asking, general question. Sorry, I had to take a drink there. If you run many workflows of the same type, same ID, they will be scheduled. So first of all, not same ID. We only one ID namespace wide. But for the same type, yeah, they get scheduled. But workflows run fast. They run a few milliseconds and like yield to the server. So rarely do you have a backlog of workflows. Usually you have a backlog of activities that those workflows are doing. So like if you don't have to use Kafka. In fact, what you schedule a workflow on, what you schedule an activity on is called a task queue. It's called a queue for a reason. It queues to work until the worker is ready to accept it. However, if you're running in a well-oiled system and your workers are properly scaled, highly available and load balanced and such, there should be no backlog. But you can have a backlog. It's very common. Speaking of metrics, you provide any pre-built Grafana dashboards. We do provide pre-built Grafana dashboards for some SDKs in some ways, but a lot of times their dashboards tend to be unique to their needs. But I'm going to defer to our dev success and general support team on that, because it's not necessarily SDK specific, though it kind of is, but that gets more into the operationalizing piece of running the workflows and workers, and a little bit less about the .NET specifics. But the answer is yes. And yes, you need to have SDK metrics on. You need to be watching those metrics, but even more so server metrics. Tristan asks, any direct experience with things like Datadog observability in a distributed workflow? Yes. And we right now support general OpenTelemetry via .NET activity sourcing, which means you could plug in any endpoint or Datadog piece into that, though I haven't tested with Datadog directly. Here's the problem, and there's a huge long README in the OpenTelemetry extension that explains this. But basically, OpenTelemetry spans and Datadog and Open Tracing before it and whatever, Jaeger, whatever. These spans are meant to run in process. They're not allowed. The spans are not allowed to start in one place and end in another. They're allowed to have children that do. But you're not allowed to end a span somewhere else from where you started it. Well, that makes it very difficult for distributed replayable software. So there's a lot of caveats that have to be explained about how workflows resume and how spans are not really allowed to resume by .NET tracing specification. But overall, yes. And you could flip on tracing inside of .NET and point it to Datadog or point it to Jaeger or whatever, and see your workflow as a trace. You just might not necessarily see the full span time, and you can see hiccups if it's rescheduled to another worker. I shouldn't say hiccups, but like you'll see a span break and potentially have a reparenting, but they'll all parent from the same parent span, assuming that you have OpenTelemetry turned on in the client. Or I should say .NET activity source, because it's abstracted in .NET, unlike just about any other language, into the language. Anonymous asks, where can we find more info about operation reliability? Our docs. So we have a lot of documentation about that, especially on the server side, and it will grow as the .NET SDK matures for the SDK side. Paul asking, can you use a generic type for a workflow class or an activity class? No. So we have to instantiate those. Well, actually, the activity you instantiate. So we don't even instantiate it. Now, the DI container may instantiate it, but the DI container can't instantiate. So the DI container can't instantiate if it doesn't know all the type arguments. And the workflow, sure, you can have abstract classes that take generics and stuff, but otherwise we need to instantiate the workflow, and the workflow needs to be instantiated via normal construction approaches. So a type argument is kind of the equivalent of an argument at instantiation time. So no, the answer is for the most part, no. However, inheritance and normal code reuse applies. So absolutely have a base class with some generic, and then have a concrete class that specifies that generic. And it's really important for our type serialization too, for those types to be more concrete on the final class as opposed to determined at the registration site. So that looks like just about it.
All right. Thank you so much, Chad, for answering the questions. Thank you, everyone, for asking the questions. If you have more questions to Chad or Temporal engineering team, please join our community Slack. And also, we share the link to temporal.net SDK samples to the chat, so check it out. Okay, thank you so much again. Happy holidays, and we'll share the recording with everyone. Bye.